This is lecture 23. You have any questions from the lesson? No? Okay. So we will continue our discussion on oscillators. Okay. And yesterday we just started oscillators. The two things which we uh, studied was that there are two kinds of analysis which we do to study the dynamics of oscillator. One is the feedback analysis, other is the negative impedance. And I told you we'll start with the feedback analysis. And under the feedback analysis, I stated the Barkhausen criterion, which states that for a block, for a feedback loop with a forward gain AS and feedback factor beta S, and literally I should say this. Okay, what it states that is the modulus at the in order to have a sustained oscillations at a given frequency omega, the loop gain of that whole loop should be equal to 1, and the phase of the loop gain at the oscillation frequency, okay, let me just put O, is 2k pi, where k is equals to 0 plus minus 1 and such. So okay, now let's start that thing with a very simple transistor level block. So let me just say now we are trying to build the oscillator and see when will it oscillate or not. Okay, this is under the feedback analysis. Means if it has a sustained oscillation, what frequency does it have, and what is the gain and other requirements of the on a simple transistor level oscillator. So this case you have input, and let me just mark it as in and out, and the gain from input to output V out by V in of S is some DC gain plus 1 plus S by omega P, where your A naught is equals to GM of the transistor times R, assuming that R is dominant with respect to the output impedance of the transistor, and omega P is equals to 1 over RC. And I'm writing this as minus A naught because this is a common source amplifier circuit, like kind of common source amplifier. Okay, so if I ask you, can I just use this single transistor and connect it like input to output, will it oscillate? Means one other thing is you may have a loop gain mod equals to 1, but you cannot have a phase of 180 degree. Okay, so that's then I will go and add another because I need a more phase. So I add another resistance and capacitor. What about connecting in 1 to in out? Out 2. Does it also have any chances of oscillation? Because the phase, you can have the phase of 180 degree, but that is at an infinite frequency. Okay, so can you say like 2 stages can be used as an oscillator or no? I have shown you like only 2 stages. At any place, because there will be a case where, okay, so the difference here is that you are I am showing you only 2 stages, and this is a single-ended circuit. If you are having 2-stage differential circuit, you can make even the oscillator work. Okay, so let's stick to that single stage for right now, and So I RC and I connect the input to the final output. So let me just make this. This is final output. So this one is out one. So okay. So the loop gain of above circuit is equals to minus A naught by 1 plus S pi omega p whole cube. Now this is under all assumptions that we are having that the capacitor, whatever the capacitor we are putting, that capacitance dominates. Okay. R and C are the dominating resistance and capacitance at the output of the each stage. So now, in order to satisfy, so let's first plot this. So I have, okay, so this one is mod of loop gain. So I have a DC is minus A naught Q. So let me, that is fine. Okay. So at DC you will have whatever the means the gain is A naught Q. So if you're plotting it will be like 20 log of A naught Q. And then you have all the poles at one particular frequency. So this will be minus 60 dB per decade. Okay. Now this is omega naught. Omega p. Now the phase of, let's plot the phasor. So okay. So what is the phase at 0? Pardon? Minus. So at DC you are having a minus sign, so you have a phase of 180 degree, right? And yeah, yeah. So that is the, so in so this is another thing. The Barkhausen criterion basically doesn't say that you are connecting here with a negative sign. Okay, this is the total gain of the loop. If you are using in a negative feedback, then you should take that 180 degree into account. Right. So here also we are not, in this loop also we are not having any specific negative. We are subtracting it from the system. Right. So the whole loop gain should have the 360 degree of phase. Okay. So okay, and let me just have, okay, this is another frequency. So where do we start as such? 180 degree, right? And okay, this will be slightly tricky. What is the phase at omega p? Minus 135 of this, so it's close to 45 degree, right? And so okay, whatever it is, close to 140 degree. And what will be in the end? This is minus 270, should go to minus 180, right? Will it be that? Minus 90. Yeah. So let me just, minus 90. So okay, let me just plot it a little bit to scale. So this is 180, 90, 0, minus 90. Okay. Right. So this, the phase is equals to 0 at some different frequency, means it all depends on A. Okay, so only when the phase is equal to 0 and the gain at that omega, whatever that frequency is equal to your gain is equals to 1, then only you will have the sustained oscillations in the system. Okay, so let's see. Okay, angle of loop gain is 180 degree minus 3 times tan inverse of, let's say omega is the frequency of oscillation, this is by omega p. Okay, and in order that this oscillate, this should be equals to 2k pi, where k is plus 0 plus minus 1. So first one we take it as 0 minus 3 tan inverse of omega naught by omega p. So omega naught is omega p times 10 of 60 degree. Okay, which is equals to root 3. So omega naught is root 3 times omega p. And at this given frequency, the mod of loop gain, so let me just mod of loop gain at j omega naught is equals to a naught cube by 1 plus your omega naught by omega p whole square is equals to 1. So this is omega naught is 3 times omega p. So you are having a naught cube by 2, sorry, this one is cube again. A naught cube by 2 cube equals to 1, which is a naught is equals to 2. Okay. So this particular circuit will have oscillations only when your A, means it will have oscillations when A naught is equals to 2 and the frequency of oscillation is equals to root 3 times the pole frequency, which is this. Okay. Now the question always is that if A naught is less than 2, what happens? If A naught is greater than 2, what happens? So if A naught is less than 2, you may, means if you start your system and A naught is less than 2, then in that particular case, you may have oscillations which are dying down. And we will work out with what amplitude and what loss do they die out when we look at real differential equations. Okay. This one is A naught is less than 2. And if A naught is greater than 2, then you may have oscillations build up. But whether these oscillations are going to be sustained oscillations at a desired frequency, that will only that can only happen, means the sustained oscillations can only happen in this particular circuit at A naught equals to 2 and your omega naught equals to root 3 by omega p, root 3 omega p. You can have a buildup of oscillations, but the final oscillations, if they are sustained in the system, it will be like that. You can always have, it means this again depends on the circuit. If the phase are not correct, you may have saturating. That can also happen. Okay, so no, when you say loop gain is equal, no, this is how can you have that? No, here no input is coming in the system. Then you are changing all the, so the whole it means this is let's say I take you, so what you are saying is let's do this experiment, right? So let's say beta factor is 1 and is coming here. Okay, this is nothing there. So let's say somehow you have an oscillation here. You start an oscillation here. You see whatever gain version at the output. The only thing is, let's say you see with the phase difference. Okay. Now the thing is, you are seeing this with the phase difference. This is a new input to your system. Okay. Now the question will always be that replacing the previous means whether you had the so if it's a linear system, right, when you it's a always like input to output linear relationship. Okay, now in any real system if you are changing the input all the time, okay, and every time you are changing the phase shift, that is what you are, because if I am having a linear system which is having a phase shift which is not equal to let's say 360 degree, then I am changing the state of the system all the time. Can that be sustained, right? That's the question. So in real system I do not see that can be sustained. The reason being is, let's say you take this inverter case only. Okay, means an ideal system I still need to see to work out the maths for that, but in real system if you are giving any sine wave and you are having a certain phase, let's say 60 degree just for example throughout this loop, right, all the states or all the voltage capacitors and all those things which are there, they are as per the phase of 60 degree. Now when you are coming back with a different phase, you are just changing all the states. Okay, so every time you are changing the means the capacitors and resistors, they are losing the periodicity of every period. So in a real system, I think that will be easier to explain that you are changing the capacitor voltage every cycle. So you are not having the periodic, means if the system is producing a periodic output, all the capacitor voltages and everything will be periodic in the system with the frequency, right? All the state variables there. Now, if you are having a phase change every time, they are no more periodic with that particular clock. So it may not be that easy. I do not know in which sense can you have that, but it is not possible in a real system like this. And regarding the maths for that, I think that will be much more involved if we can work that out. Okay. Any question? So, okay. So for this particular oscillator, we see that this is the requirement. And now let's look at where the closed loop poles of this oscillator lie. So the open loop gain is minus A naught cube by 1 plus S by omega p cube, and closed loop gain S is equals to your okay minus A naught cube 1 plus S by, so this will be this will be the case, right? Or there will be minus sign or no? Not S omega p. Pardon? In denominator it should be minus. It's like gs by 1 plus gs hs when hs in the negative feedback, right? So this one. So what you have is loop gain of closed loop S is A naught cube minus 1 plus S pi omega P whole cube plus A naught cube, right? So, oh, okay. So the closed loop poles for this oscillator poles, they are, so what you have is 1 plus S pi omega P. This is to show that where the poles lie in a closed loop system. So what you have is 1 plus S pi omega P whole cube minus 1. I'm writing this as because so that we can use the complex numbers here to find the S pi omega P is equals to minus 1 plus e power j pi plus 2k pi by 3 times A naught, okay, where your k is equals to 0, 1, 2. So S by S is equals, the poles are S is equals to minus 1 minus A naught, okay, and minus 1, oh sorry, the other one is actually e power j plus minus pi by 3. So you can work this out. So this one is simple. Let me just show you that. So what you have is minus 1 plus 2 times e power j pi by 3 plus 2k pi by 3. Okay. I think this complex number, finding the roots of a minus 1 or any number is easy to do. Okay. So when your k equals to 0, you have s equals to minus 1 plus 2 times e power j pi by 3, and yeah, the other case is k equals to 1, that is e power 2 pi by 3 plus pi by 3 is j pi, and the other one is minus 1 plus 2 power e j 4 pi by 3 plus pi by 3, so 5 pi by 3, that is equals to minus j pi by 3. So these are the three roots of the poles. And in complex plane, you can say that, so this is sigma, this one is j omega. In complex plane, these roots lie at, this one is the real one, which is minus 3 times omega p. Okay. And this one, I just have a look at it. This is minus 1 plus cosine of pi by 3 is 1 by 2 plus j, j times sine of pi by 3, which is root 3 by 2. Okay. All this is multiplied by actually omega p. So what you have is, this one is cancelled. So what you have is root 3 omega p and minus root 3 omega p. So these are your three closed loop poles in the system. Okay, and you see that for an oscillation, the oscillation frequency is root 3 times omega p, and corresponding to that, you have two poles on the j omega axis. Okay, so this is a very simple analysis of a oscillator based on negative feedback, and this oscillator works pretty fine in the sense you can make it to oscillate by having a proper means you can change R and C to get a desired frequency of oscillation. Okay. So any questions and any oscillator means I would say any of the ring oscillator. Ring is so this whole loop is called ring as such. It was connected in a circle. So any kind of ring oscillator, you can do the analysis of that. No matter how many number of stages they have, you can find the frequency of oscillation. If you can approximate their output load and the transconductance in the manner shown below. Okay, and the power, and where is the power coming? The power for this oscillation is coming from the supply. Okay, so do anyone okay, so let me ask this question. Does anyone think if I just connect this circuit and at t equals to 0, if one of the nodes is pulled to VDD, which R can be, so do you think there is any state where it will not oscillate? Means I just made this transistor. For a single thing, I found A naught gain and everything, and I just connected in the real practical sense. What will happen? Huh? Feedback will pull the node down because if when you start the circuit, what it can be. I mean, this is slightly different from the whole analysis we are going, because when you are going to design it, let's say this node is VDD, you start the circuit, so one node is pulled to VDD, then this is 0, then this is VDD, right? So the other node will pull down to ground. So it will oscillate as such. Okay, means this is another important thing when you're making an oscillator. If you're having an odd number of stages in the ring, specific to the rings, where nodes can be pulled to VDD and ground, in those cases your oscillator is, I do not know in which, the only case where it may not oscillate is where all these nodes are sitting at the same potentials. Means both input and output nodes are sitting at some VCM. In that case, it may not oscillate. Okay, so sometimes you also have a startup circuit for this oscillator so that you make it oscillate all the time. What happens in case of ring oscillator which are having an odd number of stages, even when it is sitting at some VCM, if your noise is large enough, then the noise will basically make the oscillations happen. Even if you are sitting at VCM, let's say to start with. But the same thing changes. So I was asking you, can I have, and so let me just use the same thing to show you a differential oscillator. So let me just, yeah. So this one I am talking of right now as a zero differential, is not fully differential. Okay, so what I do, these are connected. So let's say this is A, Z, A bar, Z bar, something. So the way, if I connect it in this manner, okay. So ideally you can say there are four inverters connected, but I can make this oscillator oscillate provided I enforce that condition that A and A bar are really complementary. I can do that. If I cannot enforce it, means the thing is, if you do not do anything to the circuit while designing, then it will not oscillate. So you have to enforce that relationship that A and A bar should always be complementary in the signal. Okay, why it will not oscillate? Let me just show you. So you see the connection, right? So let me just mark this as A, B, and B bar. Okay. Now look the connection A to B to Z to A bar to B bar to Z, and Z is connecting back to A, right? So what are your inverters here? Means what are the stages? A, B. So means I'm just writing what are the inputs, let's say. Okay. So A is 1, then B, then your Z and A bar are the same. Okay. And B bar. So Z and A bar is one inverter, and what is, and actually A bar and Z are one inverter. Means they are connected. So total four inverters connected in feedback. Just now I told that if let's say you are having VDD and ground as to starting, it's a steady state. Huh? It's a latch state. So you cannot. So whenever you are making any pseudo differential kind of oscillators, you need to pay attention that uh, whether it is going to oscillate or not. Pardon? Yeah. No, if you enforce that A and A bar, so let's say I make A to begin a starting condition, I make A as 1 and A bar as 0. Okay, I enforce that condition and then I start working. Then it may oscillate. Then again, the condition is it may oscillate till the time it has that thing maintained. Okay, if there is anything in the circuit which makes it to lose the gain for that condition to enforce A and A bar, then it will not oscillate. And okay, we will look into detail. And this condition can easily be enforced. Let's say I connect a cross-coupled inverter. This is going to be complemented at both the stages. Okay, so you can have even the means when you are making a zero differential oscillator with even number of stages. This is the common thing which you do. Okay, there are other things also. You will see that. So this is just to show that in your basically your loop gain analysis and everything is doing fine. But you know when you make a real circuit and you want it to oscillate, you need to take care of what is the starting condition. Okay, this is just for the steady state condition that how will it work. Okay, yeah, it will give. No, you basically look now. There are four things in the stages, right? Yeah. What do you mean by infinite? Okay, you are saying that. Let me just see. Huh? Mm, there is a no. There is a phase inversion that is there. So let me just see. So what we are saying is that A to B at maximum you get a phase difference of okay minus 180. That's minus minus everything will be plus here. That will be plus here. Then what you have is A B. Let me just look at it. B to C A to Z. Right. So this you will have at a no. So what about having it at? Okay, let's write it. This is interesting. Okay, I haven't thought that by the way. So for even stages, what do we have? We have a naught 4 by 1 plus s by omega p whole 4, right? So the phase of loop gain, sorry, this is loop gain. So the phase of loop gain is 4 times tan inverse of minus tan inverse of omega by omega p, right? And okay, let's see this. So you have, okay, whatever it is going, it will go minus 80 dB per decade. And so I will start with a zero phase here, right? And in the end, this becomes 360 degree at a very, whatever, wherever it goes. So I can have 360 degree here, and that 360 degree happens at a omega equals in at infinite frequency. So you can say that might be the reason that if you just leave it alone, it will not oscillate. Means this is guaranteed that if you do not do anything to this, if you do not have any of this in the system, you will not have it. You will not make it oscillate. Okay. But this thing is enforcing. So if you look at it in a very large scale picture, what it is enforcing. So in a feedback means A to B, you may means whatever the phase is, let's say 90 and 180. Okay. And if the A bar was 180, then you are having a 360 at the end. So in each stage you are actually giving it a 360 degree phase here, means a zero phase here at the end. So okay, means let me see that how can you satisfy the Bar-Cousins criterion with the inverters in place and then make it happen. Okay, yeah, I haven't thought about putting the Bar-Cousins criterion on this. So this is means okay. I can do this way. If you are saying it that let's say 2k, it is 2k pi. So if I put as 2k pi and I put k equals to 2, that is three whatever 720 degree, and then it turns out to be 360 degree, and you can work that out. Means I think I need to see that particular part. That why necessarily do you need to do that? Because in real sense, unless you have these inverters in place, this is not going to oscillate at all. Okay, that's a good catch. I will see how can we explain this with the Barkhausen criterion. Barkhouse, huh? They contribute some phase change there. Yeah. Okay, so interesting. Okay, so let me come back to this. Okay. Yeah. So okay, so this is the basic feedback analysis, and we will do this thing for different blocks. Now, the what are the oscillator parameters which we have? Let's look at that, because there are many. Like we need to know the frequency, amplitude of oscillation, and many other things, and how to measure the performance of oscillators. Okay, so the first one is the amplitude of oscillation, and so what do you think about the amplitude of oscillation in this oscillator? Means it is decided by what is the gain. Means GMRO you can make it what 1. Sorry, GMRO here is equals to 2. But if I want to change the means the common mode voltage surely depends on your I and where your VDD is, right? So the amplitude of oscillation. So the thing is, this is an amplitude you can always amplify also later, but that's a separate thing. So can you say something about whether this is a full scale amplitude or a limited swing amplitude? What kind of amplitude is this? This is a limited swing amplitude, right? So you can have both amplitude as a limited swing or full scale, and this can be changed based on the design or based on whether you are having a CMOS or CML circuit and what is the gain of the each stage. Okay. So, and now the thing is whether this amplitude is stable or not, whatever amplitude you have, what all parameters does it depend on? So let's say I bias this transistor for a certain GM and I naught. So when will I get the means whether that amplitude will always remain whatever I get in a ideal state or that will change. So you see this amplitude is actually in this particular case is a function of means A is a function of your bias conditions I naught, VDD and others. So if any of these parameters change, your I naught is going to change. Your amplitude is going to change. Okay. The next is frequency. So there are many things related to frequency. So in this case, the frequency of oscillation, omega oscillation, is root 3 times omega p, which is by RC. Okay. Now the thing is that in order to get a desired frequency, so for desired the variable parameters for desired frequency are R and C. Okay, vary R and C to vary frequency. So one thing is a desired one, and okay, I want a certain omega oscillation. I will choose a finite or some definite R and C. What is wrong with this also when you try to implement in real circuit? How stable is the frequency? Let me put it the question that way. Means when I say how stable is the frequency, it is asking the question how stable are the R and C value which you designed for. So if your R varies by plus minus 20% and C varies, let's say plus minus 30% or 20%, let's keep it that way, your frequency of oscillation is going to vary. So frequency of oscillation is not that stable. Stable in the sense it is varying with PVT variations. Frequency is susceptible to PVT variations. Okay. This is, yeah. In this particular circuit, the assumption which we have made, it is root 3 by RC. Okay. So what will happen in a large scale picture, it all depends on what kind of swing are you having at the gate. If I am using a GM model, a linear GM model, then I am assuming this is operating well in saturation region, everything is fine. But in large scale picture, it is surely dependent on RC. It may not be the root 3 factor, some other factor. The GM may not be a small signal GM, it's another GM. It's a large signal GM that we normally encounter with. Okay. So, pardon? Do we need to bias the circuit? Means you cannot keep this circuit biased at some DC voltage as such. So, okay, how will you bias the circuit if in case, let's say in case you have to do it? Yeah, yeah. Yeah. So let me just say, if I mean a very quick fix, I can say, let's say if in and out are the same potentials, and they are the operating potential, right? Then I can bias it with itself. I do not have to do any means. Maybe in some case you have to give that potential in the beginning. When it starts bias, you can remove it, and everything will take care of itself. Okay. But The thing is, if you are having any oscillations in the systems and you think that you can go and let's say connect with this a bias circuit, this will not work normally, because this resistor is nothing but it will change the phase at one of the nodes. So then if you take that phase change due to this resistance at one of the nodes, and then also you can satisfy the criterion, then it will oscillate for that given frequency, not what you desire. Okay. And I think you may not think of doing any AC coupling or DC coupling kind of thing here. Okay, means one might be a crazy idea, might be that I bias all these transistors with the resistor and I couple them each stage with an AC coupling capacitor. That also you can think about it, but I haven't seen that practical as such. And I haven't used that at all, so I do not know how will it perform in case of your those frequency oscillations. Okay. Now, the other thing is, since we are using the VCO as a free, like a voltage, not let's say not the voltage to frequency. Let's say I want to tune this VCO over a certain frequency range. Okay. So when I am talking of frequency, the two parameters which are important are tuning range, and the other one is tuning linearity. So let me just point out both. Okay, so what is tuning range? Is basically the overall plus delta F, or let me just put it this way, uh, variation in frequency around a nominal output frequency. Nominal output frequency, which is measured as something as delta F, where let's say, so let me just plot this. Uh, let's say my nominal frequency of operation is F nominal, and I can go, okay, so let me just mark these 2 points. I can go to 2 point, means I can have all the frequencies between these 2 points. So this is your F out. Now what is the control right now? So let me not make this as F nominal. This is your F nominal. So I can exercise some control on the oscillator, and I can vary from F1 to F2. Oh, this is again I'm putting on x-axis. F1 to F2. So this whole F1 minus delta F here is F1 minus or F2 minus F1. So when you design any VCO, you design it such that it has some tuning range. Think about it, because when you are using a VCO in a PLL, you have to vary the frequency to recover the phase and other things. No matter how exact you design, you cannot have a VCO oscillating only single frequency and breaks off if you just deviate from that control voltage. Okay, so what would be the desired desirable tuning range? Infinite. So everything is infinite right now. So you need to have a large tuning range. This is desired. Okay, and now I would ask another question. You need a large tuning range, so you control some parameter. Let me just say you control V control output. Now how would you like to have this V control? Would you like to have, let me just say something this, or something this, or let's say just put it this? Means you can go from one frequency to other frequency in by exercising some V. Now this is a very bad way I have written V control and plotted some kind of haphazard, but this one and this one are quite realistic in any scenario. It's a non-linear control. Okay, so what would you like to have? You would like to have a linear because that is easy for the maths. Let's put it that way. So that particular thing is measured as the linearity of the, so let me just say delta F by V control. Ideally you want is constant and ideal, so that you can do all the linear analysis and the system is much more predictable, much more easily controllable, I would say. I won't say that the non-linear case is not at all controllable, but linear is much easily controllable. Okay, so one part is the control part, but let me say that if you are having, so this is V control and this is F out, and the other case which let me consider is this. Okay, so this one is not touching it. Okay, F1, sorry, V1 and V1 and V2, and this is F1 and F2. Okay, so in one case you are having, in this case your KVCO is defined as delta F by V control, right? So in this case your KVCO is linear. In this case your KVCO is non-linear, or means the KVCO varies with the operating frequency. Okay, so let's say you design it at a given V0 and you got that nominal frequency F nominal, or let me just make it an interesting. So let's say you design something which has this and you get F nominal in both the cases, but now you are having a different KVCO as you shift your frequency. What will it do to loop gain? So for example, because right now you are looking at the stability of the system, because stability, so the way I told was that if you are having a non-linear frequency with respect to V control, or that F versus V control is a non-linear curve, then you will have a KVCO which is dependent on the frequency of operation. And now when you put everything in the loop, so for an ideal case you have something kind of this. Okay, and if we design or doing all nice maths, we will have a phase margin whatever we desired. So this is the phase margin at omega u. Now let's say your KVCO increases at a different frequency, means here you may have a different KVCO, or KVCO increases or reduces. So let's say if your KVCO reduces, where will my loop gain parameter and my phase margin will change? How? So loop gain parameter shifts down because that is directly proportional to this is just changing the VCO frequency versus gain. What will happen to phase margin? Curve shift left, right? Pardon? No, right now let's not talk of the phase margin. Let me just say what happened to the phase margin curve. Sorry, phase angle of it remains same. So what do you have? If it remains same, then your phase margin, depending on, you are reduced from here to here. Okay, now you can see that designing the PLL with the derivative here equals to 0 is useful, that if you shift slightly up and down, you do not go to the one end. Okay, so this KVCO factor is going to change your phase margin or other, and you need to do something about it. Okay, so let's stop here.